This is video number 1 for the Dynamics note packet in Mr. Sweeney's AP Physics C class. In this notes packet, we're going to begin looking at dynamics or forces and how they can help explain the motion of objects. To start with, we have to identify what a force is. And forces are going to be the primary concern of this unit. And a force is a push or pull that acts on an object. This push or pull that acts on an object changes the velocity of the object. So the end result is a change in velocity. And the study of forces is also known as dynamics. Forces were first described by Isaac Newton, and he wrote a book called the Principia, which was a book that laid down primarily some of the most foundational concepts in physics. And in there, he used 3 basic principles to identify how forces act and interact. These 3 principles are known as Newton's 3 laws of motion. And they form the cornerstone not only of this unit, but on further units that we'll be studying. And the unit of force is named after Newton's. And so when we quantify the push or pull that's being applied to an object or that we're studying, we use the units of Newton's to quantify that. Sticking with forces, the symbol for force is F. Again, the unit of force is the Newton, capital N. And Newton's is a derived unit, meaning it's made up of other SI base units. And this is the first derived unit that we're going to look at. And every time we say 1 Newton, what we're referring to is 1 kilogram meter per second squared. So 1 Newton is 1 kilogram meter per second squared. Forces are vectors, meaning that they always have a direction associated with them. And if we want to know how multiple forces acting on an object, how they will cause that object to move, accelerate, or how they change its velocity, we can determine this by using vector addition. So we will add the vectors together, and then the resultant vector of the forces is the force. This is called net force. So when you have figured out all the forces acting on an object, some of them may cancel out, others will add together, and the end result is referred to as net force. So let's talk about a few basic types of forces, and we're going to refer to these forces as we go on. The first one we're going to refer to is gravitational force. That is the force that's exerted upon an object by Earth's gravitational field. Please note this could be a gravitational force from other bodies besides Earth. The weight of an object is the magnitude of the net force required to balance the gravitational force of a body. And an object can have a gravitational force but not a weight. If you take the example of, say, a skydiver, when they are falling through the air, they have a gravitational force acting on them, but they do not have a weight, hence the sensation of being weightless. Normal force is the supportive force exerted upon an object in contact with another stable object. This force arises whenever one object is resting against another. There's a force acting between the two. This is the normal force. Retarding force is a generic term that refers to any force that causes the motion of an object or body to decelerate. So it's any force that causes an object to slow. Force of friction is a force between two surfaces that opposes motion. And drag force is the force that acts on a body as it moves through a fluid that opposes its motion. Tension is the force that's transmitted through a rope or a chain that's pulled taut from both ends. Applied force is a generic force that we refer to in this class. Is anything that's being applied that's outside, doesn't have a standard form. We refer to those as applied. It's the force that's applied to an object from something. Centripetal force is a center-seeking force that keeps an object in uniform circular motion. We'll talk about this in future units. And lastly, the equilibriant force is the force which would cause an object to achieve equilibrium. Each one of these forces we'll look at some point or another, but I want you to have a name for these forces as we start to talk about them. So let's talk about Newton's first law of motion. His law states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. What this means to say is that objects won't change their state of motion unless something pushes or pulls on it. The most significant aspect of Newton's first law of motion is that objects will continuously move unless something stops them. This is contrary to what we sometimes see as friction and drag force acts on most objects in our environment, causing it to appear that things come to rest. That only occurs because of the drag and frictional forces experienced. Again, just a review of what net force is. It is the resultant vector of all individual forces acting on a body. And when all forces acting on each other cancel out, the forces are balanced. In this scenario, net force is 0. And this is called equilibrium. Net force, again, the resultant of all individual forces acting on a body. Let's talk about this in specific examples. The first one being objects at rest. According to Newton's first law, they will remain at rest unless an unbalanced force acts on them. And objects in motion will remain in motion at a constant velocity unless acted upon by an unbalanced force. So whatever the object is doing, being at rest, being in motion, it will keep on in that state until something acts on it. Let's talk about inertia. Inertia is the resistance an object has to changes in its state of motion. So it's very similar to this idea of Newton's first law. That is why Newton's first law is oftentimes referred to as the law of inertia. All objects resist changes in their motion, but some objects have a tendency to resist changes more than others. Objects that resist changes in their motion more have greater mass. So the greater the mass of an object, the more that object resists changes in their motion. In fact, we could look at mass as a measurement as the amount of inertia that an object has. The more mass an object has, the more inertia the object has. Finally, forces do not keep objects moving. Inertia is what keeps objects moving. A couple of basic inertia problems. Which object has the greatest inertia? A falling leaf, a kicked soccer ball, a seated high school student, or a helium-filled balloon? It is a seated high school student, has the most mass. That will give it the most inertia. In this next example, we want to know which object has the greatest inertia. A 5 kilogram mass moving at 10 meters per second, 10 kilogram mass moving at 1 meter per second, 15 kilogram mass moving at 10 meters per second, or a 20 kilogram mass moving at 1 meter per second. All the velocities that are given here, the 10 or the 1 meters per second, they are irrelevant. The only thing that determines inertia is the mass of the object. So for 20 kilogram mass is the object, regardless of its speed, with the greatest inertia. Let's talk about free body diagrams. Free body diagrams are vector diagrams of the forces acting on an object. Forces, again, are vectors. And a net force, again, is a resultant of all forces acting on an object. An extremely important concept. And whenever we put forces on our free body diagrams, we always use newtons as the unit. The purpose of a free body diagram is to allow us to determine whether all the forces on the object balance, and if they don't, they can determine the net force. If the vector sum of all the forces is 0, there is no net force on the object. The object will maintain its current state of motion, either at rest or moving with a constant velocity. If the resultant vector sum of all forces is non-zero, then there is a net force. It has a magnitude, and the object changes its current motion, its velocity, based on this net force. Note that a change in velocity is an acceleration. So let's talk about the steps to construct a free body diagram. Step 1 is to identify the object you want to analyze. You have to make sure you have a convenient coordinate system. In most scenarios, it will be vertical and horizontal. We sketch all the forces acting on the object. And if any of these forces are not perpendicular to our chosen coordinate system, we must resolve these forces into their vector components that are parallel and perpendicular to our axes. Once we have all our forces parallel and perpendicular to each other, we can calculate net force acting on an object. Let's do an example of a free body diagram. In this picture, you can see a tightrope walker walking down a line. The weight of the tightrope walker, W, is pointing directly downwards in the vertical direction. And you have tension in both lines. Tension in the line to the left and tension in the line to the right. And these lines make an angle of 5 degrees with the horizontal. In the bottom right area, where I have my mouse, you can see an initial diagram of this showing the weight of the tightrope walker and the two tension forces acting. This is in equilibrium. This tightrope walker currently is stationary. So this object, this tightrope walker, is in equilibrium. It does have, this free body diagram does have a net force of 0. To start this, we have to take a look at our two tensions, our tension to the left and our tension to the right. Those two tensions are not parallel and perpendicular with the weight. But we can take those two tensions, the leftward one and the rightward one, and find their vector components, one being parallel to the weight and one being perpendicular to the weight. And this is exactly what we do here. We take this tension to the left, tension to the right, and we relabel it as tension to the left in the x direction, tension to the left in the y direction. Those two components are mathematically equivalent to tension to the left. And we do similarly tension to the right. We have tension to the right in the horizontal direction, tension to the right in the vertical direction. We take these two tensions in our previous free body diagram, and we want to replace this tension left, tension right with tension left in the x direction and tension left in the y direction, tension right in the x direction, tension right in the y direction, giving us a free body diagram that looks like this. Weight vertically downwards, tension left vertical, tension right vertical, pointing upwards. We have tension to the left and tension to the right, both of those being horizontal. This wraps up this video. Tomorrow we will talk more about this tightrope walker example, and we will look at further applications of free body diagrams.